Hi, my name is Mallett. My project is titled DEM Inversion Failures During Solar Flares. To understand features of the sun, it's very important to find out exactly how hot they are. But there are some pretty big problems with that. Firstly, the sun is far away. Secondly, it's kind of hard to get anyone to agree to go hold a thermometer up to it. No idea why, but we need to have alternative ways of figuring out how hot different parts of the sun are. All we can really do with the sun is just take pictures of it from satellites and from here on Earth, but it turns out that that's actually all the information we need to get a good idea of the temperatures present in the solar atmosphere. So if you've ever heard of something being referred to as red hot or white hot before, this is a lot like that. The color of an object is based on how hot it is and not just what it's made of. So what we can do is we can take pictures of the sun with cameras that are designed to only see one color or wavelength of light. Then we take those pictures, we do some math on them called DEM inversion, that's where the title of this project comes from, and we can find out how hot the sun is. Yay! Well, usually. In most places, we can find out how hot the sun is. The thing that we've discovered is that this method doesn't always work. And we found that where and when it doesn't work is actually really interesting. Solar flares are eruptions on the sun. They're kind of loop-shaped, and they release a huge amount of energy in the form of light. They are super interesting to study, but if we want to learn more about them, it would be really helpful if we understood how hot they were. And what we found is that for the biggest and brightest flares on the sun, our method doesn't work. Specifically, it doesn't work at the very tops of where the flare loops are. You can see here in these images that right after a flare happens, we get these black pixels localized right at the loop tops, which tells us that we don't know how hot the flare is right there. When we saw this, we started getting really excited. We want to find out why this is happening, and this is what we've been studying. One thing we were concerned about was saturation. Because these flares are so bright, the cameras we use might not be counting how much light they're getting correctly. At the peak of the flare, the DEMs don't converge. The flare is so bright that instrumentation artifacts make the data way too dirty to get information from. You can see this X pattern here. This is a really clear sign of diffraction, and this is just one of the many problems that is going on here. We wanted to make sure that this wasn't happening in these later images with the flare loop tops. So we took the data and we found out where there was too much light. That's these pink regions here. But as you can see, these contours don't cover the areas where the DEM inversions are failing, which implies that something more exciting could be happening. Another thing that convinced us that saturation was not the cause of this was that the program we ran to give us the DEMs told us where it was going wrong. We saw a clear distinction between the errors it gave when there was saturation or noisy data and the errors it gave at the loop tops, where it was just failing. In order to understand this a bit more, let's talk about how these DEMs are created. It's going to involve a little bit of math, but don't worry, not too much. When we take a picture in a wavelength I for any pixel in that image, its brightness is given by this equation here. Camera is just a really fancy photon counter. So on the left side, we have this data, the brightness of the pixel and that color, and on the right-hand side, we have why we got that data, and that's what we're trying to understand. The K here is called the temperature response function, and it tells us how much a plasma of a given temperature should emit light in the specific color I, and of that light, how much of it will we actually see with our camera. This part encodes both the properties of the plasma and the properties of the camera we're using to look at that plasma. Then we have the DEM, or differential emission measure. It's related to the temperature profile of the plasma we're looking at, and this is why we want to calculate it. It tells us about the temperature. So why can't we solve for it? Why are we getting these black pixels? The key is the temperature response function, K. The data that we use for solving for the DEM comes from cameras that just aren't very sensitive to the hottest parts of the sun. And flares are extremely hot, and these are the brightest and the hottest of them all that we're looking at. So these cameras may be missing the most important information that we could use to calculate the temperatures there. And also, this K function assumes typically that the plasma is looking at is at equilibrium or stable, but we're pretty sure it's not. These events are fast and violent explosions that throw up tons of material and can even cause electrical problems here on Earth, so we don't think that that assumption is valid. What we think this means is that the DEM inversion method is failing because it's not taking things into account that are really key to understanding flares. So we have some work to do. We want to study what physics might be going on in these events and finally figure out, how hot are they really? Thank you.